The thermometer hanging outside Thomas Whitmore's hut read 18 below zero. It was February 1894, and the Montana gold fields were locked in the kind of cold that made experienced prospectors question their life choices. Inside the surrounding cabins, men huddled as close to their stoves as they dared without catching fire. They wore every piece of clothing they owned. They burned wood at a rate that would bankrupt them if the cold lasted much longer. And still, their cabins were barely above freezing. Frost formed on the inside walls. Water buckets froze solid overnight. Men woke up with ice in their beards from their own frozen breath. Inside Thomas Whitmore's hut, the temperature was a comfortable 59 degrees. He sat in a single layer of wool clothing, reading a book by lamplight, occasionally adding a small piece of wood to his modest fire. His water bucket held liquid water. His walls showed no frost. The interior felt more like a cool autumn evening than the middle of a Montana winter. The temperature difference between his hut and the surrounding cabins was 41 degrees. Not 41 degrees warmer than outside, which would have been impressive enough. 41 degrees warmer than the other prospectors' cabins, which were supposedly heated structures. His hut was maintaining nearly 60 degrees, while theirs struggled to reach 18. The other prospectors had mocked Thomas's hut from the moment he started building it 6 months earlier. They'd called it the mud pile, the dirt dome, the prospector's pimple. It looked nothing like the proper cabins they'd built with milled lumber hauled in at great expense from the nearest sawmill 60 miles away. Thomas's structure was round, which was wrong. It had walls made from mud mixed with grass, which was ridiculous. And the roof was the worst part. It wasn't made of proper shingles or even sod laid over boards. It was just more mud, piled in layers over a framework of sticks, creating a dome that looked like someone had built an enormous bread oven and decided to live in it. Thomas Whitmore didn't care what it looked like. He was 68 years old and he'd been prospecting since 1849. 45 years of living rough, chasing gold and silver from California to Alaska to Montana. He'd built and lived in every type of shelter imaginable. He'd suffered through enough cold winters in inadequate cabins to know exactly what worked and what didn't. He'd also spent time among the Pueblo people in New Mexico and Arizona early in his prospecting career. He'd seen their adobe structures and learned their building techniques. He'd observed how comfortable those buildings stayed in both extreme heat and extreme cold. And he'd decided that if he was going to survive another Montana winter at his age, he needed to build something better than the standard prospector's cabin. The design he chose was based on ancient principles used by cultures around the world. In the Middle East, dome structures had been built for thousands of years. In the American Southwest, the Pueblo people had refined adobe construction over centuries. In the Mediterranean, thick-walled earthen buildings kept inhabitants cool in summer and warm in winter. All these traditions understood something that 19th-century American prospectors had forgotten or never known. Thermal mass, combined with proper insulation, created superior shelter. Thomas was adapting these ancient principles to Montana conditions, using materials available on site, and applying knowledge that most American settlers had never encountered. Construction had started in August 1893. Thomas had selected a site on a slight south-facing slope with good drainage. He'd marked out a circle 16 feet in diameter. Then he'd begun digging, excavating about 18 inches down to create a level floor below grade. This sunken floor would provide several advantages: reduced wind exposure, earth insulation on the walls, and access to the ground's more stable temperature. Modern earth-sheltered design uses the same principle, but Thomas was working from observation and traditional knowledge, not engineering textbooks. For the walls, Thomas mixed local clay soil with water and dried grass, creating a material similar to adobe, but with a higher grass content for added strength and insulation. The grass, cut from the prairie and dried in the sun, acted as reinforcement much like rebar in modern concrete. Thomas would mix a batch of mud, add handfuls of chopped grass, and mix until the grass was evenly distributed. Then he'd form the mixture into balls about the size of a human head. These mud balls, called cob in English building tradition, were stacked in courses, each course pressed firmly onto the one below to create a monolithic wall. The work was slow but required no complex tools or skills beyond patience and physical effort. The walls rose in a curve from the moment they started. Thomas wasn't building straight walls that would later support a separate roof. He was building a continuous dome where walls and roof were one structure. This required careful attention to the curve. Each course had to lean slightly inward so the wall gradually curved toward the center. Thomas used a string tied to a center stake to maintain the proper radius. As the walls rose, they inclined more steeply, eventually forming the dome. The technique was ancient, used by cultures from Mesopotamia to Mali, but it was completely foreign to the Montana prospectors who'd grown up with rectangular buildings and right angles. By the time the walls reached 6 feet, the inward curve was obvious. The other prospectors would stop by to watch and comment, "That thing's gonna collapse when you try to roof it. You can't build a roof out of mud. What happens when it rains? Whole thing will melt." Thomas just kept working. He knew from the Pueblo builders that mud, construction, properly done, was incredibly durable. Some adobe structures in the Southwest were hundreds of years old. Rain wasn't the enemy as long as you protected the vulnerable points and maintained proper drainage. The dome shape itself would shed water naturally. As the walls curved inward, Thomas incorporated a framework of wooden branches to support the mud during construction and provide additional structural integrity. He'd cut young cottonwood branches, stripped them of bark, and bent them into arcs that followed the dome's curve. These branches were embedded in the mud as each course was laid. Once the mud dried and hardened, the structure would be self-supporting, but the branches helped during construction and added tensile strength to resist cracking. Modern engineering would call this a composite material, combining the compressive strength of earth with the tensile strength of fiber reinforcement. The walls were thick, averaging about 2 feet at the base and tapering to 18 inches at the top of the dome. This massive thickness provided both structure and insulation. Dried adobe has an R value of about 2 per inch, meaning Thomas's 2-foot walls had an insulation value of roughly R24 at the base. For comparison, the Prospectors' cabins, built from single-layer boards with no insulation, had wall R values of maybe R1. Thomas's walls were 24 times more insulating, but the real advantage wasn't just insulation, it was thermal mass. Those thick walls could absorb and store enormous amounts of heat, releasing it slowly over time. This thermal mass effect meant the hut's interior temperature changed very slowly, buffered against rapid swings in outside temperature. By October, the walls had reached the point where they curved overhead, forming the roof. Thomas built a temporary wooden support in the center to hold the keystone section while it dried. He continued adding mud in courses, each one smaller in diameter than the last, spiraling toward the center. Finally, in early November, he filled the last gap at the top with a final application of mud, creating a complete dome with no seams between walls and roof. Once this dried, he removed the temporary support. The dome held. It was self-supporting, with all the compressive forces directed downward through the walls to the ground. There were no beams to sag, no joints to fail, no complex roof framing to maintain. But Thomas wasn't finished. The outside of the dome needed protection from weather. He applied a finish coat of mud, this time with less grass and more clay, creating a smoother surface that would shed water. Over this, he applied a lime whitewash, which provided additional water resistance and would need to be renewed annually. For the very top of the dome, where rain would hit most directly, Thomas created a cap from sheets of tin, forming a circle about 3 feet in diameter over the crown. This metal cap would shed rain while allowing the rest of the dome to breathe, preventing moisture buildup inside the walls. Inside, Thomas plastered the walls with a finer mud mixture, creating smooth surfaces. He built a central fireplace using stones and adobe, positioning it in the exact center of the circular floor plan. The chimney rose straight up through the dome, exiting at the peak. Thomas had built the chimney with a double wall, the inner wall carrying smoke, the outer wall filled with sand for insulation and thermal mass. This design meant the chimney itself radiated heat into the interior rather than serving purely as an exhaust. Every element of the structure was designed to capture, store, and distribute heat efficiently. The door was the only significant opening, positioned on the south side to catch maximum winter sun. Thomas built an insulated door from 2 layers of boards with sawdust packed between them. He also constructed a small porch entrance, creating an airlock that prevented cold air from rushing directly into the main space when the door opened. The prospectors' cabins had simple doors that led directly into the living space, allowing cold air to flood in every time someone entered or exited. Thomas's airlock design, traditional in cold climates from Scandinavia to Mongolia, eliminated this heat loss. He added 2 small windows, also on the south side, positioned to let in winter sunlight. The windows were small to minimize heat loss, maybe 12 inches square each, and Thomas built insulated shutters that could be closed at night. During the day, winter sun would stream through these windows, warming the floor and walls. At night, the shutters closed, preventing heat loss through the glass. This passive solar design, capturing free heat from the sun, was another traditional technique that the prospectors' cabins ignored. Their windows were placed for convenience and light, not for thermal performance. By the time Thomas moved into his hut in late November, he'd created a structure that embodied centuries of building wisdom from multiple cultures. The prospectors saw a mud hut. Engineers would have seen a thermally efficient, passive solar, earth-integrated dwelling with massive thermal storage capacity and minimal heat loss. The performance difference between the 2 perspectives became obvious when the real cold arrived in December. If you're fascinated by traditional building methods that outperformed modern construction, make sure to subscribe to the channel. We're uncovering lost knowledge that kept people comfortable in extreme conditions, using nothing but local materials and ancient wisdom. Hit that subscribe button so you don't miss our next episode. The first serious cold snap came in mid-December. Temperatures dropped to 5 below zero and stayed there for a week. The prospectors' cabins, with their thin walls and conventional construction, lost heat almost as fast as their stoves could generate it. Men burned firewood constantly, creating roaring fires that consumed wood at an alarming rate. Even then, the cabins were cold. They might reach 40 or 45 degrees near the stove, dropping to near freezing in the corners farthest from the heat. The temperature distribution was extremely uneven. You could be sweating on the side facing the stove while your back was freezing. Thomas's hut behaved completely differently. He'd light a modest fire in the morning, burning perhaps 1/10 of the wood the other prospectors used. The fire would warm the thermal mass of the floor, walls, and central chimney. These masses would absorb the heat and begin radiating it back into the space. By afternoon, with the fire reduced to coals and winter sun streaming through the south windows, the interior temperature would climb to around 55 to 60 degrees. The thick walls, once warmed, held this heat for hours. Even letting the fire go completely out overnight, the temperature inside would only drop to 48 or 50 degrees by morning. The thermal mass released its stored heat slowly, keeping the space comfortable. The prospectors noticed. They saw smoke from Thomas's chimney for maybe 2 or 3 hours per day, while theirs poured smoke continuously. They knew he was using far less wood, but assumed he must be freezing. A few of the friendlier prospectors stopped by to check on the old man, worried he might be suffering in silence. When Thomas opened the door, warm air greeted them. Stepping inside was like entering a different world. It was genuinely warm. The air was comfortable. There was no temperature gradient from hot near the stove to freezing in the corners. The entire space was evenly heated. The visitors stood in confusion. How was this possible? Where was the massive fire? Where were the cords of stacked wood? Thomas explained the principles as best he could to men with no background in thermal dynamics. The thick walls hold heat like a storage battery. The dome shape means no corners where cold air can pool. The central fire heats all the walls equally. The thermal mass releases heat slowly over many hours. The sunken floor and earth contact provides insulation. The south-facing windows capture free solar heat during the day. It all works together. The prospectors nodded, but many didn't truly understand. They just knew it worked, and they were jealous. When the temperature dropped to 18 below in February, the performance difference became even more dramatic. A prospector named Jim Hudson, who lived in one of the nicer cabins, bought a thermometer and started taking measurements. He measured the outside temperature. He measured his cabin's interior temperature with the stove running hot. Then he asked Thomas if he could measure inside the hut. Thomas agreed. The results were startling. Outside, 18 below zero. Hudson's cabin with a roaring fire, 17 degrees above zero. Thomas's hut with a small fire that had been out for 3 hours, 59 degrees. The difference between the hut and the cabin was 41 degrees. Hudson showed his measurements to the other prospectors. Some didn't believe it. They thought the thermometer was broken or Hudson had made a mistake. Several went to check for themselves. They all got the same results. Thomas's mud roof hut was maintaining temperatures 40 to 45 degrees higher than their cabins, and doing it with a fraction of the wood consumption. The implications were significant. Wood gathering was hard, dangerous work. Every cord of wood represented hours of labor with axe and saw. The prospectors were burning 10 to 12 cords of wood per winter. Thomas was burning maybe 2 cords. That was 8 to 10 cords of wood, not cut, not hauled, not split. That was weeks of labor saved. That was money saved if you were buying wood. That was the difference between barely surviving winter and living comfortably. The prospectors started asking questions. Could they retrofit their cabins with thicker walls? Could they add adobe insulation to existing structures? Could they build huts like Thomas's for next winter? Thomas answered patiently. Retrofitting was difficult. The prospectors' cabins were fundamentally the wrong design. Rectangular structures with thin walls and conventional roofs couldn't easily be converted to thermal mass systems. But building new structures using his methods was certainly possible. He'd be happy to teach anyone who wanted to learn. Several prospectors took him up on the offer. In the spring of 1894, 4 prospectors began constructing huts based on Thomas's design. He supervised and advised, teaching them the mud mixing ratios, the proper dome curve, the importance of thermal mass, and all the details he'd learned over decades. The work was harder than building conventional cabins. It required more time and more physical labor, but the materials were free, available right on site. No expensive milled lumber to purchase and haul, no complex carpentry skills required, just mud, grass, water, time, and effort. By fall, all 4 huts were complete. When winter came, the prospectors who'd built them experienced the same comfort Thomas had. Warm, even temperatures with minimal wood consumption. They became advocates for the design, telling other prospectors how well it worked. But adoption remained slow. Most prospectors stuck with conventional cabins. Why? Several reasons. First, the mud huts looked strange. They weren't what people expected a home to look like. There was social stigma attached to living in what appeared to be a pile of mud. Men took pride in their cabins, often using them as status symbols. A well-built wooden cabin with glass windows and a proper roof said you were successful. A mud hut said you were poor or eccentric. Second, the construction method was unfamiliar and seemed risky. What if you built it wrong and it collapsed? What if it leaked? What if it fell apart after one winter? The perceived risk seemed high compared to conventional construction methods that everyone understood. Third, there was a belief that modern materials must be superior to primitive ones. Milled lumber was a manufactured product that required industry and infrastructure to produce. Mud was just dirt. Surely the manufactured product must be better than dirt. This assumption was wrong, but it was deeply ingrained. Fourth, building a dome required commitment to a location. The structure was essentially permanent. You couldn't disassemble it and move it if the gold played out. Prospectors often thought of their presence as temporary. They'd work a claim for a season or two, then move on. A conventional cabin could be abandoned without much guilt. A mud hut represented more invested effort, making it psychologically harder to walk away from. Fifth, wood frame construction was familiar. Most prospectors had grown up around such buildings. They knew how to build them, how to repair them, how they worked. Mud construction required learning new skills and trusting a method that was foreign to their experience. The learning curve created resistance. Despite these barriers, the mud hut design spread slowly through the mining community. By 1896, perhaps 15 or 20 prospectors in the district had built variations on Thomas's design. All reported dramatically improved comfort and reduced wood consumption. A few made improvements on the basic design. One prospector, a man named Chen Wei who'd emigrated from China, incorporated design elements from traditional Chinese earth buildings, creating a hybrid structure that combined Thomas's dome with elements of a Yao Dong, the cave dwellings of northern China. His version performed even better than Thomas's original, maintaining comfortable temperatures with almost no heating at all. Another prospector, a Swede named Anders Lundgren, built multiple small domes connected by short tunnels, creating a compound that segregated different functions: sleeping, cooking, storage. This modular approach meant heat could be concentrated in the area being used while other areas stayed cool, further reducing energy needs. These innovations demonstrated that the basic principle, thermal mass plus insulation in an efficient form, could be adapted and refined in many ways. The design wasn't rigid, it was a set of principles that could be applied flexibly. The mining company that operated the larger claims in the area took notice. They were spending significant money on firewood for their worker housing. The standard bunkhouses they'd built were expensive to heat. In 1897, the company commissioned Thomas to supervise construction of earth-sheltered dormitories for their workers. Thomas designed long rectangular structures built partially underground with thick earth walls and vaulted roofs. These weren't perfect domes like his hut, but they incorporated the same principles: thermal mass, insulation, passive solar, orientation, and earth contact. The structures worked well, providing comfortable housing for 40 workers while reducing the company's firewood costs by over 60%. The success of these company buildings might have led to wider adoption, if not for the decline of the mining district. By 1900, the easily accessible gold was mostly played out. Prospectors moved on to new strikes in Alaska and Nevada. The population of the Montana district shrank from over 500 at its peak to less than 50 by 1905. The mud huts were abandoned, along with the conventional cabins. Some collapsed over the years from lack of maintenance. Others simply melted back into the earth as rain and freeze-thaw cycles gradually eroded the walls. By 1920, little evidence remained that the structures had ever existed. Thomas Whitmore himself moved to California in 1899, seeking a warmer climate in his advancing age. He died there in 1906 at age 80. Having spent 57 years as a prospector and seen the complete boom and bust cycle of multiple mining districts. His mud roof hut, which had kept him comfortable through 5 Montana winters, stood empty for a few years before the roof collapsed inward. By 1910, it was just a circular mound with no clear indication it had once been a dwelling. The knowledge Thomas had preserved and demonstrated was lost again, surviving only in the memories of the few prospectors who'd built similar structures and then dispersed to mining camps across the West. The principles Thomas used weren't lost to history entirely. They continued to be used in traditional cultures around the world. Adobe construction never stopped in the American Southwest, though it declined in popularity during the 20th century as people equated modern materials with progress. In the Middle East, Africa, and Asia, earth building remained common, though often stigmatized as backward by people aspiring to Western-style construction. The knowledge existed, but it was marginalized, seen as something poor people did because they couldn't afford modern materials, not as a potentially superior building method worthy of study and preservation. The revival of interest in earth building began in the 1970s, driven by the energy crisis, environmental awareness, and the counterculture's skepticism of mainstream practices. Architects and builders began studying traditional earth construction, recognizing its advantages: low embodied energy, excellent thermal performance, use of local materials, durability, and low cost. Books were published, workshops were taught, demonstration buildings were constructed. The same techniques that Thomas Whitmore had used in Montana in 1893 were being rediscovered, tested, and validated by modern building science. Thermal imaging confirmed the superior heat retention. Energy monitoring showed the reduced heating and cooling loads. Structural testing proved the durability. Today, earth building is recognized as a viable, sustainable construction method. Organizations like the Earth Building Association promote best practices. Building codes in some jurisdictions now include provisions for earth construction. Modern variations like compressed earth blocks, rammed earth, and stabilized adobe have emerged, combining traditional principles with modern quality control and engineering. But traditional hand-formed cob, the method Thomas used, is still practiced by enthusiasts and owner-builders who value the low-cost and hands-on, accessible nature of the technique. You don't need expensive equipment or specialized skills. You need understanding of principles, attention to detail, and willingness to do the work. The thermal performance advantages Thomas demonstrated in 1894 have been confirmed by modern testing. A properly designed earth building can maintain comfortable interior temperatures with minimal or no heating in moderate climates and with greatly reduced heating in cold climates. The thermal mass effect, storing heat during the day and releasing it at night, or storing heat from heating events and releasing it over many hours, creates temperature stability that conventional lightweight construction cannot match. The even distribution of radiant heat from warmed thermal mass is more comfortable than convective heat from forced air systems. The thermal inertia, resistance to temperature change, means interior conditions remain stable despite wide swings in exterior temperature. Before we wrap up, I want to ask you to subscribe if you haven't already. We're bringing back building knowledge that was mocked in its time but proved vastly superior to conventional methods. Your support keeps us researching these forgotten techniques. Hit that subscribe button now. The 41-degree temperature difference between Thomas's hut and the prospectors' cabins wasn't magic or luck. It was physics. The massive thermal mass of the thick earth walls and floor-absorbed heat from the fire and solar gain. The excellent insulation provided by 2 feet of earth prevented heat loss to the exterior. The dome shape minimized surface area for a given volume, reducing heat loss. The earth contact and sunken floor provided additional insulation and access to the ground's stable temperature. The central fireplace radiated heat evenly to all walls. The passive solar orientation captured free heat from winter sun. All these factors working together created a structure that was simply better at maintaining comfortable temperatures than the thin-walled rectangular cabins the other prospectors built. Modern building could learn from this. Most contemporary construction prioritizes appearance, construction speed, and initial cost over thermal performance and life cycle value. We build houses that look good but perform poorly, requiring constant energy input to maintain comfort.
We've forgotten or ignored the lessons that traditional builders like Thomas understood. Thermal mass matters, insulation matters, building form matters, orientation matters. Using these principles doesn't require abandoning modern materials or returning to primitive living. It requires integrating the best of traditional wisdom with the best of modern technology. Some modern architects are doing exactly this. The earth-sheltered houses of Malcolm Wells, the passive house movement in Europe, the work of architects like Rick Joy who use rammed earth in contemporary designs. These practitioners demonstrate that earth building can be modern, beautiful, and high-performing, but they remain a small minority. Mainstream construction continues to ignore thermal mass, prioritizing lightweight framing and active HVAC systems over passive thermal design. We could build houses that, like Thomas's hut, maintain comfortable temperatures with minimal energy input. We choose not to because of industry inertia, building code barriers, and cultural expectations about what a house should look like. The prospectors who mocked Thomas's mud roof hut made a natural mistake. They judged based on appearances and preconceptions rather than performance. The hut looked primitive, therefore it must be inferior. This assumption was disproven by objective measurements. The hut was 41 degrees warmer. That wasn't opinion or perception. It was measured fact. Yet even with this evidence, most prospectors stuck with conventional construction. Changing deeply held beliefs is difficult even when confronted with contradictory evidence. Humans resist changing their worldview. It's easier to dismiss anomalies than to revise fundamental assumptions. This pattern repeats throughout history. Good ideas are often mocked initially because they don't fit existing paradigms. The mockers aren't stupid or malicious. They're working from incomplete information and cultural conditioning that tells them what should work and what shouldn't. When reality contradicts their assumptions, the cognitive dissonance is uncomfortable. Some people resolve this by updating their beliefs. Most don't. They dismiss the contradictory evidence, create justifications for why it doesn't matter, or simply ignore it. The prospectors who built mud huts updated their beliefs. The majority who stuck with wooden cabins found reasons why the mud huts didn't count or weren't relevant to them. This is why knowledge preservation is so important. If only the innovators know something, that knowledge is vulnerable. When they die or move on, it can be lost. If knowledge spreads widely enough to become embedded in a culture, it becomes resilient. The knowledge of earth building survived in cultures where it remained common practice. It was lost in American mining camps where it was adopted by only a few individuals. The scale of knowledge diffusion determines whether it persists or disappears. This is why documentation matters. Why teaching matters. Why creating communities of practice matters. Knowledge exists not just in books, but in living traditions passed from person to person. When the chain breaks, knowledge dies. Thomas Whitmore's mud roof hut demonstrated principles that could have transformed frontier housing. It provided superior comfort with lower cost and less labor than conventional construction. It used local materials and simple techniques accessible to anyone. It worked in harsh climates where conventional structures struggled. Every prospector who saw the measured 41-degree temperature difference knew it worked. Yet the knowledge didn't spread widely. It was lost when the mining district depopulated. The same lessons had to be relearned decades later by the alternative building movement. This loss and rediscovery cycle represents waste. Wasted effort, wasted suffering, wasted resources. We keep reinventing solutions that already existed because we failed to preserve and transmit knowledge across generations. The story of the mud roof hut that held 41 degrees more heat is a story about evidence versus assumptions, performance versus appearances, and the difficulty of changing established practices even when better alternatives exist. It's about an old prospector who applied ancient wisdom in a new context and achieved results that shocked his contemporaries. It's about the gap between what works and what people believe works. And it's about how easily valuable knowledge can be lost when it depends on a few individuals rather than being embedded in a culture's common practice. These lessons extend far beyond building design.
They apply to any field where traditional knowledge exists alongside modern practices, where assumptions guide decisions more than evidence, where the old way might actually be better than the new way, but nobody checks because everyone assumes progress only moves forward. The thermometer reading that showed 41 degrees difference wasn't just a number. It was proof that we don't always know what we think we know, that primitive doesn't mean inferior, that solutions from the past can outperform solutions from the present, that we should measure and test rather than assume, and that sometimes the person everyone mocks turns out to be the only one who understood what actually worked.